All right. Hello, everybody. 42 Recitation 9. As usual, it's me, Justin. What's up? Oh, the projector's on. Hold on a sec. Should be good now. Okay. All right. Yeah. Everybody see that? Cool. All right. So, first problem that we're gonna be doing is another like non-dimensional thing. This time we're gonna be non-dimensionalizing a couple of like differential equations, specifically the continuity equation and the momentum equation. And so we're given the problem, consider the interpressible continuity and momentum equations with constant viscosity. Find the non-dimensional forms of these equations. Use the characteristic velocity u and characteristic length L. We're going to be using those two to go about doing all this. So first off, the continuity equation, it's just a fancy way of saying like conservation of mass. Same concept as that. It's a gradient relation thing. And before we get going, just to make the notation easier and make it easier for you guys to understand, I'll say this. We're going to assume only in x direction. Right? So that'll make our lives a little easier when we go to like expand out these gradient operator stuff for the PDEs. So the other thing, so we've got this characteristic velocity and characteristic length, right? In terms of like an experiment that we're running, these are like reference values that we're taking, right? So, if I'm measuring the flow over an airfoil or something, the characteristic velocity might be the free stream velocity, right? Just a constant term that we know. And then the length might be like the length of the airfoil, just, a length that we know for sure and just kind of describes how the experiment will go, right? So that's pretty much it for this first one. For the continuity equation, the math is really easy, and it's not doesn't really give you an appreciation of how useful this thing is. But so we want to start off first is I'm going to rewrite this gradient.v into its like partial differential form. So let's go continuity. So by definition, this gradient, del.v is just the gradient of the velocity. So we can rewrite this as partial v over, like I said, we're assuming only an x direction to make the numbers nicer. So for partial x equals 0. And so now we want to say, okay, how do we make this thing non-dimensional? Right. The v and the x in here are dimensional numbers. We have like meters per second and meters or something. Well, we do that by defining some non-dimensional reference variables, right? So for x, we'll say x star equals. Now, how do I make what relation do I have? So this x star, this is basically a pi group. All right, same thing you can think of like as a pi group. So how do I make this non-dimensional? I have some x length, right, that I'm solving for, this x here. Just divide it by L, and it's non-dimensional. So we call it x over L. And so also by definition, so we can substitute things in later, we have x star times L is what x actually equals. Now we do the same thing for the velocity. Let's say v star equals, what are we going to do here? Well, we've got our v over u, right? Because we're given a characteristic velocity, so we're going to use that. And so again, we have v equals v star times u. Cool. Now plug this back in. So we have partial, what's our v? It's v star times u over partial, what's our x? It's x star times L equals 0. And now again, so inside of these partial differential things, right, these del operator terms, we have two different terms, right? We have one that's like the v star, the x star, blah, blah. And then we also have a u and an L. Those u and an L are constants, right? We already said those are constants. So we can just bring those out. So we have u over L times partial v star or partial x star equals 0, right? And that u over L, though, that's still a dimensional term. So what we're going to do, we're just going to divide by u over L to the other side. 0 over u over L is just 0. So we're left with partial v star or partial x star equals 0. We can also rewrite this in terms of the general form. We can also rewrite this as gradient star dot v star, right? Equals 0. Cool. Like I said, first one, it's not really all that special, all that fun. The second one that we're going to do is way more mathy, way more really makes you think about what's really going on and shows you how useful it is, right? So let's get into that. So let's do the momentum equation. Before we do anything, again, let's say what's constant, right? Let's pick out our constants. So our constants, again, we have u and L, but in the momentum equation, we also have a density term. We're assuming that to be constant, and also a viscosity term, mu. So those are our constants. And what are our variables? Well, everything else. So we've got we have a t as a variable, right? We have a v, we have a p, and our x, right? But we already know the v and the x, right? So v equals v star times u, and what? X equals x star times L, right? And now, so let's try and non-dimensionalize the time and the pressure. So let's go T star equals, how do I non-dimensionalize this, right? I'm going to have some T up top, and T is in seconds. So I know I'm going to have some seconds in the denominator. So I have to have the U up top and then the L down below to get rid of the length from the U, right? So with that, let's do math again. For T equals T star L over U. And similarly, for pressure, we say P star equals what? Well, I've got some pressure up top. Now, what kind of math do I have to divide this? Well, I know I have some constant rho, right? And then I also have a velocity. Well, if you remember from your Bernoulli's equation, you have like P plus 1/2 rho v squared, blah, blah, blah. If you lap off the 1/2 from the start of that, you have a rho v squared, a density times a squared velocity. So that's a pressure term right there. If you do the math for that, those are units of pressure. Same thing, we can just divide by rho u squared. So we get P equals P star times rho u squared. Cool. All right. So now we have all of our bid time non-dimensionalization stuff out of the way. So now we're going to plug in. And I'm just going to rewrite it fast in terms of because I don't like those del operators and stuff. So let's just rewrite it real fast. Equals rho g. And we're going to be stuck with this rho g term for a while. That's okay. Minus partial p, partial x, plus mu, gradient squared v, right? And it's super important thing. Let me actually zoom in a little bit so you guys can see a little better. So super important thing, all right? See how this squared is being applied to the x, right? Whereas up top, the squared is being applied to the del operator. Super important. So when you go to plug in what our x equals, it's x star times L, you'd have like an x star squared L squared when you go and expand it. Super, super important. It's not just hanging out there for shits and gigs, right? It actually means something. So let's go plug everything in. So we have a rho times what's our v? It's, what v star times L or times U over D. What's our T? It's T star L over U. Oh, I have to be writing really small, but that's fine. Equals, we're stuck with this rho G for a while. And also, my thing differs from the T slightly. The T does some clever manipulation where they can get rid of this rho G. I'll show you my way of doing it. Because we also get another useful relation that'll be good for you guys to know for the future. But anyway, if you see the T actually really sucks, like I was saying. So this is, write stuff like this down. But whatever. We're stuck with this for now. Now minus, we have our del, and what's our P? P star rho U squared over at star times L plus mu, and then partial squared. V is V star, V star U over partial at star L all squared, right? Now let's still expand this out. All right, expand stuff out, factor out constants. Okay, what are our constants? Let's look in this first one, this row term. So we've got a U here, and we've got an L over U down here. So the bottom U would flip up and be a U squared. So we can factor out a U squared over L. So the whole thing would get a rho U squared over L times D V star over DT star, right? And then that equals, still we're stuck with the rho G. And then subtract, again, we can pull out a rho U squared and an L times partial P star, partial F star. Now plus mu, we've got a U up top over, like I said, L squared. We're going to bring on L squared because we're applying the square to that term right there. And then times partial squared B star over partial at star squared. Cool. And so now we're going to do some more manipulation. Let's go. I'm going to skip a line. I'm going to start skipping lines too because it's getting kind of cluttered. So you can see we've got a lot of like terms here. So let's divide by rho U squared over L. Cool. So let's do that. So we get stuck with a dv star dt star equals. So if I divide by a rho U squared over L, see this term, those cancel. So we get a GL over U squared minus that whole term just goes away, so that's sweet. And then plus, if you do all this stuff, right, factor all this stuff out, cancel what you can, you get stuck with a rho or mu over rho UL times partial squared V partial at star squared, which, you did something right because, that mu over rho UL, that sure damn looks familiar, don't it? All right. It's 1 over Reynolds number. And so now we can say, let's clean stuff up. We know, right? We know mu over rho UL equals 1 over Reynolds number, right? And we also know, you guys don't know this, but I know this. We also know that FR, so there's another non-dimensional number called a Froude number, okay, the Froude number. Similar concept to Reynolds number, right? It just describes certain aspects of a flow. Don't worry about it too much, but Froude number is equal to U over root GL. So wouldn't you know it? Look at that. That's just 1 over Froude number squared, right? So go plug everything in. And I'm also going to turn these back into their like del form. So it'll be like, like gradient squared v, instead of the partial operators. So plug everything back in. Um, so for finiteness, we have d v star over d t star equals 1 over Froude number squared minus gradient star p star plus 1 over Reynolds number um, gradient star squared v star. Cool. And we're done. Right? So this is really powerful because this whole thing is totally non-dimensional now. So I can be doing some experiment in my lab here in Tempe, and I can go and get these non-dimensional values solving this equation, and I can give it to my buddy in New York or whatever in his fluids lab, and he can run the same experiment with his setup, right? He might have different length scales, things like that, but it doesn't matter because this whole thing is non-dimensional. I say, hey, right, if this spits out some number, whatever answer this spits out, it'll be like a ratio of his length scale to his number he got, right? And it all governs the same stuff. So it's super nice having these non-dimensional things because my lab conditions might not match his, right? He might have a bigger wind tunnel, but it doesn't matter because it all governs the same stuff because it's non-dimensional. Nature doesn't care about how big of a wind tunnel you've got. Nature doesn't know what the hell a meter is, right? What the hell is a meter? I don't know. Anyway, cool. Any questions with that? Cool, cool, cool. Yeah, it's just non-dimensionalized. It's really handy, especially if you take like a actual partial differential equations class. Shout out Dr. HP. I got 100 on his PDE exam. Boom, boom. Go. Anyway, yeah, you do a lot of like non-dimensional stuff. You mostly deal with like the non-dimensional versions of stuff because it's how you get the general solution to things. Um, anyway, but all right, yeah. Any questions before we move on to part two? Question two. Sweet. All right, question two is about pipe flows and things like that. How much pipe flow stuff y'all talk about? Like head loss and stuff like that. Nothing, no pipe flow stuff. Well, we'll go over a little bit of pipe flow stuff. So, here's the problem we got here. All right. So, I'll just read the problem statement before I explain anything. So we've got oil with density 900 kilograms per cubic meter, and kinematic viscosity of 0.0002 meters squared per second flows upward through an inclined pipe. Pressure and elevation are known at sections 1 and 2, which are 10 meters apart. Assuming steady laminar flow, A, verify that the flow is up. B, compute HF. HF is the head loss between points 1 and 2. And compute C, Q, the volumetric flow rate, V, the velocity, and the Reynolds number with respect to diameter. And is the flow really laminar? All right, so what we're going to be doing, the base equation for this is an equation that's very similar to Bernoulli's equation. Kind of comes from the same sort of stuff, but now we're not assuming that the flow is like perfectly inviscid, right? We're assuming that there's some friction loss inside of this pipe. What that friction loss is, you guys don't know yet. You'll figure that out in probably a week or two, how to actually calculate that. But for now, we just know, hey, we're pumping water or oil through this pipe, and we know that in the ideal case, it can go X number of meters, right? But I go, hey, when I actually go and pipe this stuff, it only goes slightly less than that. And so what are we losing here? We're losing what's called head loss, right? There's two different forms of this equation you'll see. The one we're doing now, all the terms are in like a length scale, right? All the terms come out to be like meters, things like that. So that's the head loss form. There's also the pressure loss form, which, shocker, spits out pressure terms, right? If you care more about how much pressure you're losing instead of how much like potential pumping height you're losing, right? Put it in pressure form. But anyway, so for part A is kind of stupid. Um, the T has some way of going about improving it. This is what I'm gonna say, right? For part A, clearly fluids flow from high to low pressure. So flow must be up. Right? So flow must be upwards from 1 to 2 because we have 350 kilopascals down here and 250 kilopascals up here. I mean, you can't. I mean, it's just how it works, man. It's just physics. You know, things go from high to low pressure. So I feel wind. Same thing with water, or oil. It's all fluids. Fluids behave like fluids. Cool. All right, now for part B. So, for part B, this is the head loss version of the equation I was just talking about. Like I said, it's spooky similar to Bernoulli's equation. It's P1 over rho G plus V1 squared over 2G plus Z1 equals P2 over rho G plus V2 squared over 2G plus Z2 plus HF, where this HF is that head loss term that we're talking about. Because like I said, there's some friction or something going on in there that's making us lose a little bit of height. So we need this HF term over here to balance all the stuff. So this does indeed still equal out to being a constant number. So anyway, like we said before, we're assuming it's constant, steady flow, whatever. So the velocity inside of this pipe is constant, right? So when we go and solve for HF, those V's go away, right? You're just subtracting by the same value, so those go away. Same thing, Z1, we're calling this down here Z1, so Z1 is 0. So really the only thing we need to know is Z2, where Z2 just equals 10 times sine 40 degrees, right? It's just the vertical distance of this pipe, right? Where 10 is hypotenuse, whatever. So Z2 equals like 6.43 meters. Now solve for HF. So we have HF equals P1 over rho G minus P2 rho G minus Z2. All right, you know all the numbers here. We're given everything. We have HF equal to 4.89 meters. 4.89 meters of head loss, which is actually kind of big for this small of a pipe. Yeah, yeah. But anyway, so that's like the Bernoulli's ish equation for this. In the head loss form, like I said, if they wanted like a pressure difference, right? If they didn't give us the pressures and we know like the pressure loss or something, you can cleverly multiply by rho g all over and isolate the pressure terms. On it too much. I'll just show you some math behind it. I don't want to sit here and explain all the concepts behind it if you guys haven't learned any of it. But anyway, so for part C is where things, since you haven't learned any of this stuff, part C is kind of hand wavy. All right. So part C, to find Q, to find our volume flow rate, right? For Q, we know flow is laminar, or we assume flow is laminar. So we use the laminar flow equation for Q. where this will be given to you. All right. And so Q for a laminar flow. Yeah, he'll sit there and derive this, I'm sure. Don't ask me to derive it. There's a lot of calculus behind it. But anyway, Q is pi times rho G d to the fourth HF all over 128 mu L. Right? And where mu, so mu is what? Nu times density, right? Should be something like that. I believe. Yeah, because yeah. Yep. Yeah. So go plug everything in. You end up getting Q equals 0.0076 cubic meters per second, right? And now for velocity, nothing tricky here. We know V equals Q over A. And we're given a diameter, right? We know the diameter. So V equals 2.7 meters per second. And lastly, we want the Reynolds number with respect to the diameter, which we're given kinematic viscosity, so we're going to write it in that form. RED is velocity times diameter over kinematic viscosity. So to plug this in, should be about 810. And again, that's non-dimensional. There's no units on that. It's Reynolds number. And now lastly, is it laminar? Is it actually laminar? We go, well, transition point for pipe flow, turbulent transition point. And again, you'll learn this. Right. So the turbulent transition point for pipes occurs at approximately Reynolds number of 2300. Okay. Our RED is approximately 810. All right. Which ours is less than 2300. All right. It's less than 2300. So yes, it's probably laminar. And I say probably because Reynolds number is the only thing that determines something's turbulent or not, right? I could have a nice, easy going, smooth flow, but if I drop a rock in the middle of it, it's going to make it pretty turbulent pretty quick, right? Even though the velocity itself isn't going too crazy. Anyway. But yeah, for this case, assuming there's no funny business going on, yes, we can say it's laminar. That's about it with that. Your professor will go over all of this stuff in much more depth. It's just a quick, sample calculation math stuff going on. Don't get too worried about it. All this stuff's very pluggy chuggy, as you can see. You've got a set of equations that you'll use. We give you these parameters. You have to find these other parameters, plug them in. It's not too bad. Not too bad. Any questions? All good? Cool. All right. Online, if anybody has any questions, shoot me an email. If not, have a good one.